Hello everyone, my name is Feng Rizwa.
I'm Ben Leverett.
I'm Rahil Ajani.
My name is Komodit Taniwatkun.
And this is the Infectious Disease Exposure Alerting Device. For short, IDED.
Due to the coronavirus pandemic, we wanted to create something that would help prevent the spread of this deadly virus. We thought it would be important to use proximity to determine risk, so we decided to use the Bluetooth Received Signal Strength Indicator, or RSSI.
The idea behind using the RSSI is that we are able to measure the proximity between a healthy person and an infected area or an infected person. We believe that as long as the proximity is higher, the risk of being infected with the disease is also higher. RSSI helps us accomplish just that. We're able to get the RSSI reading, which reflects the distance between one device to another, and this will help us track, alert, and monitor the spread potentially of the coronavirus around the world when people are using our device.
This slide shows the project incubation period, where our idea was submitted on March 21st, and other companies had similar ideas in the following weeks.
In order to do this project, we use the knowledge of RSSI, which is a measurement of the power present in the received radio signal. Besides, RSSI is an indication of the power level being received by the receiving radio after the antenna and possible cable loss. Therefore, the greater volume of RSSI, the stronger of the signal is, as you can see on the table number 1. Moreover, RSSI can be used to approximate distance, but it is not precise, as you can see on figure number 1.
For our project, we're using the command mode built into the Bluetooth module. Although it is not introduced in the lab, the Bluetooth module we have in the lab kit has the capability of this receiving AT command string, a serial string from the embed, and respond with a unique data and its identifiers and ends with an OK. For our particular example, we're using AT plus BLE get RSSI, and the Bluetooth will respond back to us with a negative number, which is the RSSI reading, and an OK. We can use data processing techniques to process the data and parse through the numbers and get the useful information for our application.
This diagram is a representation of the software implemented to build this system. We used an RTOS with multiple threads where the main thread receives and parses the AT commands given from the Bluetooth. Then we print the risk level on the ULCD dependent on the risk and if it changes. Then we also blink the LED corresponding to that risk level. We alert the user using the speaker when the risk level changes, and we also log the SD card whenever the risk level changes, showing the time, the risk level, and the RSSI values corresponding to that risk level.
These slides show the hardware component that we use in our project.
For future improvements, we would like to remove our main constraint by using a central mode Bluetooth module as opposed to the peripheral mode Bluetooth module in our kit. The central mode Bluetooth module has advantages of broadcasting and advertising data, as well as reading RSSI values without connecting to a device. We would also like to be able to implement the real time on a mobile device by getting that mobile device's time for recording the data.
We want to encode device ID into BLE packets and create apps for Android and Apple. We also want to improve data logging efficiency and back it up to a backend server using C#.
And that concludes our project and presentation. I want to thank you very much for your attention, and hopefully I'll see you next semester.
Thank you. Have a nice day.